Good morning. I'm actually representing both NOAA as well as the University of Colorado. And being an employee of the university means I'm not a government employee, so I can say some things that maybe a NOAA employee couldn't say. Hopefully I won't say too much of that. The previous talk that I much enjoyed actually reminded me that the team I'm on used to be called CSI. It was the climate scene investigation. Because one thing we do is we try and attribute causes to extreme events. So an extreme event, like a crime, is also something like it happens in nature, and we're trying to figure out how much of what's going on is something that would have gone on anyway, and how much of that is caused by humans. The other person, so that's Stephanie Herring, who actually was originally asked to give this talk, and I represent her view as well. And Marty Hurling is my conspirator-in-chief, if you will. He's actually leading that team, and we have had quite a few papers together. I have a little collection here of extreme events that range near and far. The one on the left was taken right between this place and my home above Jamestown. There was a flood we had in September 2013 where Boulder got about a year's worth of rain in 5 days. These kind of things, of course, can happen, and they actually change landscapes. They certainly change the road. The one next to it on the right shows the snow cover and ice extent in early March 2014. The winter of 2013-14, from December to March, was the coldest in about a century in that region. That was something we didn't expect to happen, and it still can happen. The next one, of course, is a typhoon bearing down somewhere on Southeast Asia, taken from the space station. And then the right one is one that we hopefully won't see in Estes Park. Those are 2 twisters in Nebraska. So those are the kind of things that people think of when they talk about extreme events, but of course there are also others like droughts that take much longer to evolve and have similar impacts. Let's see whether this works. Yeah. So I'll talk a little bit about climate change. I assume, this being an international audience, that there won't be too many people that doubt that there's climate change. I could give a separate talk on justifying that. I will actually show a few slides on that. I will talk a bit about extreme events, how we define them, how these types of events, how well are they documented over the last, say, century, and how well do we know whether the frequency of the occurrence is changing. And then, of course, the big question is how much of that can be attributed to climate change. There's the little detail that it probably interests you, which is the impact on ecosystems. Like I said, when you have a 1,000-year flood, you rearrange a canyon, so you're changing the landscape. That's a very severe impact, but others are more subtle. And so there's actually this whole group that I am with. It's about the same size as the previous climate CSI. We have about 20 people, and we are trying to understand, and we actually publish a report every year on various extreme events around the world. A lot of focus on the US, where the data is most readily available, but we're very open to looking at things outside the US to understand what happened and why. So one climate change slide. April 2016 was the warmest in recorded history globally, especially over land. Some of that was the big El Nino we just had, so not all of this is climate change, but it's certainly ominous. And you could argue that some of the data is contaminated. We don't have perfect records, especially when you go back in time. The way we used to measure temperatures and where we measured it has changed. So there are these little error bars around there that I'm not showing here. But when you get an anomaly in April 2016 of 1.9 degrees Celsius, almost 4 degrees Fahrenheit over land, you can be assured that at least 3/4 of that is real. And then there's an error bar around that. And of course, one thing that we know, and this is just a correlation, not a causality, is that this coincides with ever-rising greenhouse gases. Here's just the CO2 part of it. Other greenhouse gases are actually growing faster. And mind you, the relationship is not really that linear, so this is a bit simple-minded here. There was also a peak, for instance, in the 1930s that is not explained by that, and you could argue that some of that was the reduction in aerosols during the Great Depression era, then when the skies cleared up a bit worldwide and made it possible to get warmer, and then from 1940 to 1970, when most of the world was like China is today, we put a lot of pollution into the atmosphere, and that indeed makes it a bit cooler. So there are these indicators, I can't even remember where Stephanie got this from, but there are these indicators that we have that show that climate is changing. Temperatures are going up, not just at the surface, but also higher up in the atmosphere. They're going up in the oceans. I've circled both snow cover and sea ice, so we'll get back to that, where the evidence is actually a little bit more complicated. But glaciers, for instance, are disappearing in most of the world. Another thing is that you can actually reproduce these changes in a computer model. So we're using a bunch of runs with the so-called GEOS5 system, where we're basically reproducing both the temperature change that's observed over the last 100 years, as well as the changes in humidity. Now, humidity, or the amount of moisture in the air, is a key ingredient of climate change. One thing is that it amplifies the CO2 effect directly, so you get a bigger bang for the buck if you increase greenhouse gases. You also, because of the moisture holding capacity of the air, you have more moisture in the atmosphere on average, and that in turn amplifies the warming, especially at night. And so far we're talking maybe 5% globally. The problem is that these numbers are exponential, so it will keep going up the way we are going. So just to clarify this in terms of sea ice and snow cover, on the left top you see a curve that is probably very hard to see from the back, but I guess you will all get these PowerPoints, so you can look at this at leisure. And I have the link here for both of these sets of graphs. On the left, that's the Snow and Ice Data Center. You can actually pick any year you want since 1979 and overlay it. And what you see here is that it's hard to see. So you can see the current year, which is on track to be a record low sea ice year. So even the winter was quite low. And then you can see, I think, 2012, which is the most extreme low-end year. And I think the other one I have, and I can't read this here, I think it was in the 1980s, the last time we were close to normal. I think 1996, I'm sorry. 1996, I think, is that year. So it has been about 20 years since we had a near normal sea ice year. That's in the Arctic, that's in the northern hemisphere. So very clearly a decline in sea ice and very closely linked to climate change. In the southern hemisphere, we actually just recently had the record year in the 2010s. It's actually hard to keep track. We have had multiple years with near record levels. So right at the same time that we get the minimum in the northern hemisphere, we have been actually getting an enormous amount of sea ice in the southern hemisphere. Some of that could be variability, just natural variability. Some of that could be that the Antarctic sea ice is being helped along by higher precipitation over the Antarctic continent and more ice carving coming off the continent. So that's basically still something that we have to investigate and understand. And on the right side, we have the snow cover. And many of you have seen the green curve, which is the bottom right, which shows the decline in spring snow cover, which is part of the change in the phenology we're seeing, where spring is coming earlier in the northern hemisphere at least, and it goes along with having less snow. The complicating thing with snow is that it gets contaminated by soot and aerosols. So the fact that we have a lot of pollution still going on, say coming from China, for instance, that stuff gets trapped in the snow in the end. And we have actually a similar problem in Colorado where we get dust storms. We get more dust storms than we used to get. And when you see dust on snow, not so much this year, but recently in 2009 was spectacular, even up here in Estes Park. It makes the snow dirty, and more importantly, it makes it darker, so which means it makes it melt faster. So some of this could be totally independent of temperatures. And as you can see, for the Northern Hemisphere in the fall and winter, we are not really seeing that much of a trend. So there's still a lot of research to be done here. This is a much more technical talk. I apologize, but I figure some of you may enjoy it, and others may be able to read up on it later on. And I have a lot of links here, so you can follow up on it. And of course, you can also contact me. So we have here, for instance, we have the bell curve we just saw earlier, and a simple-minded way of thinking of how the climate is changing is to just shift it to the right, right? If it gets warmer, everything on the right side gets more likely, and on the left side gets less likely. Some people have argued that the extremes are getting bigger, which really means that you are changing the curvature, if you will, of the bell curve. So you're making the tails bigger, which means that both the red and the blue, in this case, the cold and the warm, is getting more likely. And then the third one is my favorite, which is, I think, closer to the truth, where not only are we seeing a shift towards warmer, but we're also seeing a shift in the distribution of this curve. And in this particular case, we still inflate the tails a bit, and that means that you still get these cold events. You're not out of it. You still get the 2013-14 in North America, or 2009-10 in Eurasia, where you get a really cold winter, even though you didn't expect it. But on the other hand, those warm events are getting more and more likely. I guess India just set a new record high temperature just a few days ago. That's the kind of thing I'm talking about here. Here's a paper by Judah Cohn and co-authors in Nature Geoscience, where they looked at some of these extreme measures that we often look at. So the top left two figures show basically the change in precipitation over the last, 50 years or so. And where it's blue, it means that it has gotten wetter. So basically, once you get away from the deserts further north, it has gotten wetter. And the second figure on the left shows how the fraction of those events that come from heavy precipitation events has gotten higher. And then the third one on the left is basically the change in the number of what we call warm days, so on the top 10%, so the hot days where you have to turn on your air conditioning if you have it. And you can again see that in Eurasia, this has really increased the most. There is this funny area in the southeastern part of the US where it actually hasn't increased, and that correlates pretty well with the area that has started to irrigate massively over the last 50 years. And some of you may realize that if you irrigate your fields, you get a higher yield, but you're also cooling down the air because now you have some of the sun's energy goes into evaporating instead of heating up the air. So it's kind of curious that the southeastern US is also the part of the world where a lot of people don't believe in climate change because they don't feel it. You have to look beyond your backyard to understand this. Bottom figure shows that's the number of warm summer months, again in the upper 10%, and you can see this big increase. This is for the region 20 to 50 north, so it's that belt north of the desert into the mid-latitude where we actually have pretty decent observational coverage, so we have a lot of stations to report on this, and you can see that the warm months have increased. The warm months obviously were defined early on in the early part of the record. So we get a lot of hot summer months. Let me skip over the top right one, but then the last three are kind of interesting. So those are measures of cold. And you can see how the coldest day of the year, for instance, which is a second figure, has warmed up. On average, the temperature that you get, the coldest temperature of the year you get has warmed up by a few degrees Celsius. And then in the last 10 years, it has gone down again. Okay. The next figure shows the number of icing days, or days where the high temperature is below freezing, very clearly something where not much happens in nature. And again, we hit a minimum just before 2000, has gone up again. And then the bottom line, that's a count of the coldest winter months. And again, those have gone up again too. Well, what's going on? And this is really a matter of debate. There are some people who believe that sea ice is causing all this, and it's part of climate change, and it's irreversible. And others are saying, well, wait a minute, 20 years ago, we had a switch in the frequency of the North Atlantic Oscillation or the Arctic Oscillation. So the zonal wind across the Atlantic or the strength of the jet stream has changed, and you get a lot more blocking events. And that's why we have seen a lot of these cool downs. So this is still undecided, how much of this is climate change and how much of this is natural variability. I apologize, a lot of these figures have a US focus because that's where we have the most data, but we are trying to expand our scope. So this is probably not unique to the US either. So one thing we did, we had a paper in 2013 where we looked per decade at heat waves, which were like 4 days above 95th percentile or something, and then cold waves where you get, so these are not individual days, but strings of days that are really cold. And to us, we kind of thought that the 1930s would still stick out, the great Dust Bowl era in the US where we had the hottest temperatures. And that's still sticking out there, that we haven't reached that level yet. And I was a bit surprised at the 1980s, which was a period, I was in Wisconsin, at the University of Wisconsin, and I suffered through some amazingly cold winter. Chicago actually set an all-time record low of 3 years in a row, 82, 83, and 85. So that's actually another one of those where we don't really understand how these cold waves came about, and that's part of that enigma that we're still investigating. Floods and droughts. It is very hard. Again, we have fairly good records in the US. The USGS maintains tens of thousands of stream gauges, but there's only about 200 that are reasonably pristine, i.e. they're not affected by upstream development, damming, and so forth, or subdivisions that were built nearby the gauge. So there are about 200 gauges that have a 100-year record where you can look at how has the annual flood discharge changed, the extreme flow. And you can see that east of here, so around, that's I think the 95th meridian, so from the upper Midwest to New England, the runoff has increased. We are getting bigger flows, but in the Southwest, including in this part of the world, actually it has decreased over the last 100 years. So it's not unequivocal. Everybody is getting the same output. Same thing when you classify drought. This is using the Palmer Drought Severity Index that combines temperature and precipitation. So when it's hotter, it also gets more severe. And you can see that the 1930s in the US at least was actually still the most drought-prone era. That's why it's called the Dust Bowl in the last century. And if you do a 100-year trend through this, you don't see an uptick or a downturn. But if you go over the last 30 years, over the last 40 years, you can see the 2000s have had quite a few droughts. And that last tick mark there is 2012. So we're sort of inching our way back up to the 1930s, but we haven't exceeded it yet. So the US is really maybe a bit unique in that. I think there are other parts of the world where it's more straightforward. So one summary figure we had in this paper with Peterson et al. That was in the Bulletin of the American Meteorological Society in 2013, is we looked at all these different extreme events and classified them in terms of detection, in terms of being able to document what's going on, and attribution, which means we understand what's causing these changes. So I mentioned precipitation events or flood events, heat waves, cold waves, floods and droughts. There are others. I showed you earlier this picture of hurricanes and tornadoes where it's a bit more complicated. So remember Katrina? Remember 2005 and 2004 when Florida got hit by all those hurricanes? There was a lot of talk back then that, oh, this is climate change and we are in deep doo-doo. And it turns out that actually since then it hasn't really been that extreme. And there was a raging debate, and it has been tabled so far. We basically have all decided we need more data, where we're saying, yes, the Atlantic has had this uptick, but some of that is the warming of the North Atlantic. If you go elsewhere, and here's the North Pacific, for instance, the bottom figure, then you can see that actually there have been these changes that go up and down, but we're not really seeing an uptick. The bottom line on this is, in terms of the modeling evidence, is that there's a small indication that the most extreme hurricanes and typhoons you can get may be getting stronger. And that's part of that whole story with having more moisture that fuels the energy of these systems. But we're not really clear whether we're going to get more or less events. And in the end, if you look at insurance damages or whatever, the number is also what counts. You're probably aware that we haven't had too many landfalling systems in quite a while in the US. So hurricanes right now, actually, in the last IPCC report, they sort of punted on that. They said, let's wait a bit and let's not get carried away. It is not that clear-cut which way it's going. Tornadoes. Well, there is this problem that now we have more people that can identify a tornado, and they actually document it, right? People have their iPhones everywhere. So if you look at the blue line on top, that shows the number of F0, or the weakest tornado category in the US, and it looks like it's going up. Well, I think this is a case of sampling, right? So you have more people that actually see these than before and report them. People didn't used to go online and report these. We didn't have online 30 years ago. If you look at the red dots, those are the stronger ones that actually have damage to buildings and people, and those red dots are actually pretty flat. So the number, don't believe the story that we're getting more severe weather or more tornadoes. It is not, the evidence is not there. It might still happen, but right now we're not seeing that. And the problem is that aside from humidity, the other two things that determine severe weather and tornadoes is the wind shear and the vertical stability. So if you are, for instance, if you're warming up the air above the ground more than near the ground, then you're actually increasing the stability, and it makes it harder for thunderstorms to develop. If you have a forest fire, for instance, we see this occasionally here. We had this in 2012, in 2002, and I think last year with the Canadian fires and the Pacific Northwest fires. When you get a lot of smoke in the air, you're actually letting less sunlight go through, and it actually makes it harder for the ground to warm up enough to create a thunderstorm. So we often actually have a dry summer in times when we have a lot of forest fires going around. And they don't even have to be local. I mean, those from last year were from Canada. They were 1,000 miles away, and they still created this haze that made it harder to get thunderstorms. So it's very murky, and the evidence, like I said, with the observations, is we don't have a very good history on that. Finally, drought. We have now a system in place. In fact, there's one for global data using satellite data and what little observational data we have to determine where we have drought conditions, and they're standardized. We now have a system to grade these droughts from D0 to D4. Southern California here is D4 as of April. But we don't have much of a record. This goes back to 1999. That's it. That's a very short record to understand climate change. So what can we expect? Well, we are in, if you look at the last 15 years, if you look at the emissions of greenhouse gases, we are on track for the highest end scenario, which is what they call our representative concentration pathway 8.5. I can't make this up. And which basically means we're going to triple the amount of CO2 in the air in the next 100 years. The way things are going, I would be surprised if we manage to end up below that. I mean, that's what we all hope, but it doesn't look like it. What does that mean? We end up with, in 1 century, this is in the middle of that graph goes all the way to 2300. If you go to 2100, we're warming up by about 4 degrees Celsius or 7 degrees Fahrenheit. That's a lot. That's the average. Basically what this means is the average climate is going to be as warm as the warmest season that you've ever experienced. So a big change is coming down the pike. What does that mean in terms of extreme events? Again, the these are different pathways. It's always the most extreme, the red line that we're talking about here. So it looks like cold waves will eventually get weaker. Part of that is that eventually it will be too warm to create snow cover in the mid-latitudes. That's really what this story is. We will have fewer cold days, more wet spells. We will have more hot days as in the kind that can kill you if you don't have any way of cooling off. And the precipitation you get in those wet days is going to be more. The bottom one is basically summarizing this. We're looking at 20-year events. So what are the odds of getting a 20-year event? And by 2100 on the bottom right, those shades mean that we're getting a 20-year event every 5 years instead of every 20. All of these things are summarized. I'm just giving 2 references. I was part of this assessment. We basically looked at different regions of the US. I was part of the Southwest team. And then there's one international report from the SREX that also looked at this. And I'm finally getting to the impact on natural resources or parks. And of course, the most easily understood impacts are on wildfires and related to that, droughts and floods. And so you should care about this. This is not just some esoteric academic topic. And I apologize on this short notice. I was only able to get 2 slides here that specifically address your concerns. But obviously, with the earlier spring that we're seeing globally, you have changes in wildlife behavior, right? You have an earlier start of migration. You get an earlier phenology. The phenological seasons have changed, so you get flowers to come in earlier and so forth. And we have this we have a problem bear in my neighborhood that came out of hibernation, very hungry because last year was very bad, and he came out very early, even though it wasn't even that warm. Species may disappear if you have one of those isolated parks. I was thinking of like the Black Hills in South Dakota, which have the top of that is pretty much isolated from the rest of the Rocky Mountains. And so there's no easy way for animals to migrate in and out. So those kind of places will have trouble because these changes will be big. And well, we went through all this around here. We had 2002, initially, it was the worst fire season, and 2012 was even worse, although that was more because there were more people in harm's way. But we have had the forest fires after a big 3-year drought, and we have had the pine beetle kills that basically have run their course. They've basically eaten everything they could. Of course, those outbreaks, pine beetle outbreaks are a function of having a drought because the trees don't have enough juice ability or insecticides for that matter, to get rid of these animals, of these insects. And the secondary effect, so this is one of those little feedbacks, is that the CO2 uptake by these ecosystems is going down, which means that you keep more CO2 in the air. How am I doing on time? I'm almost done, but yeah. Okay, so need to summarize what I was saying. Are all extreme weather events caused by climate change? Sometimes when you look at the media, you get these 2 camps. One saying, oh, none of this is all natural variability, and the other ones are saying, oh, it's all climate change and the sky is falling. And the truth, of course, is in between. And that's where our team comes in, where we're actually trying to understand what is going on and how much can we really attribute to climate change. One thing that is happening, though, is that the odds of certain things are changing, of certain extreme events, and we are pushing the boundary. So if you make it warmer and have a rain event, it's essentially exponential to the tune of every 10 degrees Celsius, you're doubling the amount of moisture in the air. So if you have a thunderstorm at 10 degrees C higher than before, you can have double the amount of rain for the same storm. And that's one of those big problems we're seeing. Natural climate variability, which is actually how I started 30 years ago, was to look at El Nino, La Nina. We just had a very big El Nino happening, and it did some very strange things. It kept Arizona and Southern California dry, and Seattle had the wettest El Nino winter ever. So It was not quite what we expected. Here in Colorado, it behaved very well. We had exactly what we expected, plus a little bit of warming. So in October, we had a big storm that should have been a snowstorm, and it was a rainstorm. But otherwise, and we've had a lot of snow this spring, very typical for El Nino. Sometimes you have to combine these things. So one good example is in 2009-10, we had the most extreme blocked flow over the Atlantic. At the same time, we had the last El Nino, and that's how you get big snowstorms on the eastern seaboard, which is, of course, for the national media, that's all that matters. So if Washington, Rimmer Snowmageddon and all those things, that happened because of that combination of El Nino and the most extreme negative NAO. This last winter, we had an El Nino, and there were only 2 weeks where the North Atlantic was blocked, and voila, they had one big snowstorm that shut everything down. So it really works quite well. But it was all natural variability. So I mentioned earlier that we have these reports we write, and there's actually a whole issue, a special issue of the Bulletin of the American Meteorological Society that comes out once a year, and here the covers for 2013 and 14. I cropped them funny so they looked like they're different sizes. They were normal 8.5 by 11s. And we did a paper on the floods 2 years ago. Then I laid a paper on the Midwestern winter that was really interesting to understand. And we just submitted one on the extreme rainfall events of last year. That one, we tried to have a global focus and scope. And we have about 1,000 stations in the US that have 100 years of nearly complete daily rainfall data. Being a native of Germany, I know that they have many more stations like that, but they don't share them that nicely. So it's very hard to get daily data from other countries. Australia is pretty good about this, Canada, a little bit of South Africa, but it's very hard. So we gave up on global, but we would love to do this on a global scale. So here's just this one example of the snow cover story. And I don't have time really to get into this, but basically what you're seeing at the bottom left is the change in snow cover in the models. The coupled models, they're saying it's going downhill, and until about 2000 it was pretty level, and in the future we will get less and less snow. And what you're seeing on the top is the observed. And so in the last 20 years, instead of going down, we have had some winters with near record snow cover, and that's what enabled that big cold winter. And the relationship between snow and temperatures is well modeled. It's just that the models think that the snow cover should disappear, and it's not doing that yet. It's an interesting conundrum, because eventually it will happen, but not yet. The rainfall extremes, I just want to point out that the most extreme events we had last year were the May floods in Texas, and then the Mississippi floods, the central US floods in December. And what's interesting about those, and that's sort of in these figures, that was not part of a trend. So they came out of the blue. And that's, of course, you get the biggest impact of an extreme event if you have nothing to prepare you for it. The most extreme example here is not even in these figures. South Carolina had that October event where a hurricane was offshore and it rained 15 to 20 inches in South Carolina, and they have actually seen a downward trend in these extreme events, and so they were very ill prepared. The levees and dams were not in good shape, and they had disproportionate amount of damage. They shouldn't have that much damage. Just to end on a nice note, after all this gloom and doom, one thing that is working, in the US at least, is there is a climate reference network that's being built that has stations that are in more or less pristine environments where we're trying to preserve the landscape as it is, and so national parks are a perfect environment for that. So there are 24 stations that have now been set up across mostly the western US. And you could call it a collaboration for the ages. So there's one here, one example in the Grand Tetons and one in Denali. That's all I have. Thank you.
We're willing to take some questions?
Sure.
I think we've got about 5 minutes for questions or so. One in the middle here.
It's 13 minutes, I think.
Thank you. Bill Westerfield from Wyoming State Parks. Do you think the loss of pine needles from the beetle kill trees has had any effect on the earlier snow melt from the mountains?
I'm actually part of, I didn't talk about this, but there's a paper that just came out last year with Ben Livneh, Livneh. He's the lead author, where we looked at both the impact of dust on snow and the impact of the pine beetle outbreak, because it was so huge. And as you probably know, there are these different stages that the trees go through. You know, once the needles die, they stay on the tree first, then they get blown off. So we have the red stage, the gray stage. The net effect, as you probably know as well, is that you end up with a little bit more runoff, because a tree that's still standing is still providing some shade, but you have less interception, so you get less of the snow to get stuck to the needles and branches and falls to the ground, but it still gets the shade and the protection from the wind. That changes once the tree falls over. So it's a very complicated evolution, you know. So initially, I don't think there's that much effect, except that the tree, when it's dead, doesn't evapotranspire as much, so you lose less through the tree itself. Then when the needles are off, you get a gain, and then when the tree falls over, then the wind scours it out again. So it's a complicated story, and there's actually some debate as to what the effect is. It's probably just a few percentage points. But right now, we are, I think, in a stage where we're getting a bit more runoff than we would have expected because of the pine beetles.
Another question? No more questions? Well, thank you very much. Klaus, I have a gift for you.